Hi everyone. Today we are going through Le Chatelier's principle. This is going to be lesson 4.4. Now, when I was in grade 12 chemistry, I learned how to pronounce this by calling it Le Chatelier's principle. So, was not a very French accent that I was taught in. So Le Chatelier is a better way to say it, Le Chatelier's principle. So yeah, let's learn it. Okay, so what this principle does is it describes how a chemical equilibrium shifts in response to a stress or a disturbance within an enclosed system. So basically you've got a system, it's at equilibrium, it's happy, and then something happens to change the equilibrium, to push the equilibrium, or to stress the equilibrium. Now, the system will end up shifting to restore equilibrium, and this is called, and so that is Le Chatelier's principle, when you have shifts in equilibrium like that. So an example of this are hopefully, maybe some of you will know what this is, definitely. This is a mood ring. So mood rings change color, and the theory is that it changes color according to your mood. Now, of course, that's not rooted in science at all. And what's actually changing the color of a mood ring? Some of you will know, yeah, it's temperature. So as we have shifts in temperature, we get different colors that are showing up. So that would be, so the system is at equilibrium. When you put it on your finger, the ring on your finger, it's going to heat up, and then that's going to shift the equilibrium. So, and we'll do examples that will show how this works here. Okay, so a stress, first of all, is a factor that causes a shift in equilibrium. So we talked about temperature there, but there's a whole bunch of different, well, not a whole bunch, there's a few stressors that we can talk about here. So whenever a stress is placed on a system at equilibrium, the system shifts in the direction that partially removes this stress. So remember, we've got a system at equilibrium. I'm just going to show A is in equilibrium with B. So when we have a stress, it's going to either shift to the right or shift to the left to change the equilibrium. Now, remember, we've got our KQ, which is our products over reactants. So we know that equilibrium moves, right? So it's a measure of, KQ is then a measure of products over reactants. So those concentrations can change. Sorry, I just realized my son is texting me. I got a phone call from his school saying he wasn't in class, but apparently he is in class. Now I have to tell him to talk to his teacher. Okay, anyways. All right, types of stressors then. Hold on one second here. Oh my God. Okay, sorry. Okay, so changing concentration of either reactants or the product. So this is the first kind of stress that we're going to talk about. So changing concentration of either the reactants or the products. So if we've got this system here, we've got A plus B is in equilibrium with C plus D. And so the question is, what effect does the addition of some A have on the equilibrium concentrations of B, C, and D? So what this means is we are taking the concentration of A and we are increasing it. So A is increasing. The concentration of A is increasing. So the question, what will that do to equilibrium? Now remember, the system is at equilibrium, which means we've got a forward reaction and a reverse reaction happening at the same time. So, forward reaction and the reverse happening. We don't know where equilibrium lies. It could be, if we think of it as a sliding scale, right, where we've got A and B over here, C and D over here. We don't know exactly where equilibrium is. It could be anywhere along here, right? So anywhere between those 2 points is where equilibrium is. So my question then, if we increase A, what happens? So we have to just think of this, and again, try to visualize this actually happening here. So A and B are reacting together to form C plus D. At the same time, C and D are reacting together to form A plus B. So we've got both reactions happening. Now, if I increase A, what am I going to do to the possibility of A reacting with B. Now remember, A plus B, those two are reacting together. So if I increase one of those, I'm increasing the possibility of those two things to react, right? So if it increases the forward reaction then, so if I'm making it so that it's more likely that A and B are going to react, what's going to happen is you are going to drive equilibrium to the right. So it's going to shift to the right. So it's going to shift to the right, and this will relieve the stress of extra A. Because when we shift to the right, if we drive the forward reaction forward, A now is going to be depleted. What happens to the concentration of B if equilibrium is shifted forward? B is going to decrease. The concentration of C and D, meanwhile, if we are driving equilibrium forward, we're pushing that forward reaction, that means that more C and D are going to be produced. So C and D are going to be increased. So the concentrations of C and D will increase while B will decrease in this particular example here. And if I was in person, I'll do this for you when I see you guys next, I would sort of think of A gets big, so this gets big, and then we sort of push over to the right. And I would kind of mime pushing over, which oddly really helps people sort of figure this out. Oops, yikes. The stress is more A. To remove this, equilibrium will shift to the right. Therefore, B will decrease while C and D will increase. That's what I wrote anyways, but there you go. Okay, so number 2 stressor is volume changes. So this is only for gas. Now, we've got NH3 is in equilibrium with N2 plus H2. So the question is, what effect will a decrease in volume have on the equilibrium concentrations? So if we are decreasing the volume, now remember, pressure and volume are inversely related, and we know that because of, oh, where's my picture? Boyle's law. That didn't come up properly. We have Boyle's law, so we know that pressure and volume are inversely related. You would have taken that in your grade 11 course here. So if the volume is decreased, this means pressure increases. So just keep that in mind here. So the question is, which way is equilibrium going to go? So we've got this system here of gases. We have a decrease of volume. So you want to look at this and you want to think, well, how many molecules do I have on each side? So I've got 2 here, and I've got 3 plus 1 is 4 over here. So if I look, the left-hand side, or the reactant side of this equation, has less gas molecules. So equilibrium is going to shift left where there are less gas molecules. To the left, to the left. We're going to go to the left here, which means equilibrium goes to the left, which means what happens to the concentration of NH3? So when I say it goes to the left, what I mean by that is the reverse reaction is now favored, okay? So we favor the reverse reaction, so the concentration of NH3 is going to increase, and at the same time, the concentration of N2 and H2 will decrease. Okay, third situation here is temperature changes. This is the one we talked about right at the beginning here. So in order to answer these ones, you would need to know whether a reaction is endothermic or exothermic. So looking at this, is this endo or exothermic? Take a look at it. So heat is on the reactant side there. So the forward reaction here is endothermic. The reverse reaction is exothermic, okay? So they're opposite to each other there. So what effect does an increase in temperature have on the equilibrium concentrations? So what that means, heat is going to increase. So you've got lots of heat here. So what happens to the concentrations of M, N, and R? Now, if we increase the heat, if you look at the forward reactions, the forward reaction is moving that way. So this is our M plus N. M plus N, in order for them to react, it requires heat. So if you give more heat, if you increase the temperature, that's going to favor that reaction. So it's going to push the forward reaction. So what's then going to happen to the concentrations of M and N? They're going to decrease because you're pushing the forward reaction, or equilibrium is shifting to the right. So we're going to say it shifts right. And this would lead to then, so the forward reaction, so equilibrium shifts right, so what that means is M and N are going to decrease here. Now R is going to increase because you're driving that forward reaction first, but one thing that's important to remember is that increasing the temperature increases kinetic energy, which increases collision. So just because of that, both rates are actually going to increase here. However, though, the forward reaction is going to increase more. So that's going to be the dominant force here. Okay, so this question here is KQ larger or smaller as the temperature increases? So to do this, you want to remember, that KQ is equal to products over reactants. So if we increase the temperature, we've said that equilibrium shifts right, which means this gets bigger while these get smaller. So what's going to happen to KQ? It gets larger. Yep, because the products are going to increase while the reactants decrease here. Okay, so these are the kinds of questions you're going to have to answer where, this question here is KQ larger or smaller. You have to know quite a few things to be able to answer that question, right? So it's theoretical, but you have to really understand what's going on in the system at equilibrium here to answer that question. Now, number 4 is catalysts. So A plus B is in equilibrium with C. So what effect does a catalyst have on the equilibrium concentrations? Now, reminder, what does a catalyst do? A catalyst is going to speed up an equation, right? So what effect will it have on equilibrium? None. It's a trick. There's no stress here. It just speeds up the rate. So there's not going to be a shift in equilibrium. It's just going to make everything happen faster. Number 5 is the addition of an inert gas. So what is an inert gas? An inert gas are the noble gases. These are gases that will not react with anything. So what effect is that going to have on an equilibrium system? No change, again, as it doesn't take part in the reaction, Okay, so there's really only 3 stressors that we put in those extra 2, apparently just to trick you. So concentration changes, volume or pressure changes, and temperature. So those are the 3 main stresses that you need to be aware of and know how Le Chatelier principle is used to address those stresses. Okay, we're going to work through an example here. So I've got methane plus water. So first of all, the forward reaction here is endothermic because it requires the energy here, right? So we're just going to go through and figure out what's going to happen. So predict the equilibrium shift. So you're going to be commenting here whether they shift to the right or shift to the left. So you should probably pause the video and see if you can answer these on your own before I go through them. Okay, so predict the equilibrium shifts that result from. So if we increase the temperature, if I increase the temperature, I'm increasing the energy that's required for the forward reaction. So the forward reaction is going to be favored and we are going to shift to the right. Now, if I decrease the temperature, the opposite is going to happen. If I decrease the temperature, I've slowed down that forward reaction because the forward reaction needs that heat. And so in that case, the reverse reaction is going to be favored. So this is going to be to the left. Now, if I decrease the pressure, decreasing the pressure would mean increasing the volume, which means I've got more space. So if I've got lots of space, I am going to go to the side like it's me. the equilibrium system is going to shift to the side that has more gas particles. So we've got 4 on this side, 3 plus 1, and we've got 2 over here, so it's going to shift to the right. Now, if we decrease the volume, now it's the opposite of C here. If I decrease the volume, it's going to go to the side with less gas particles, so it's going to shift to the left. And then this next one I find interesting here. What happens if we add calcium chloride? So calcium chloride is something that's going to react with water. So if I'm adding CaCl2, calcium chloride, and it's reacting with water, what am I doing to the concentration of H2? I'm taking it out, right? So I'm adding something that's going to bond with the water, which means the concentration of water is going to decrease. Because that decreases, I'm going to slow down the forward reaction, because the forward reaction is our methane here plus water. So if I take away water, that's going to be happening less, which means it's going to shift to the left. So the reverse reaction would be favored in that situation. Okay, again, try this one on your own, pause the video. Okay, so now predict the effect of the following on the equilibrium concentrations of the CH3OH. So I'm specifically looking at that, okay? So if I decrease the temperature, now this one is noted by energy here. So this forward reaction here is exothermic and the reverse reaction is endothermic in this particular example here. So looking at the energy here, if I decrease the energy, that means the reverse reaction will not be favored because I've lowered that. So it's going to be the forward reaction, it's going to shift to the right, and the concentration of CH3OH is going to increase. Now, if I increase the pressure, increasing the pressure means decreasing the volume, which means I don't have a lot of space. I've got 3-to-1 here, so if I don't have a lot of space, it's going to go shift to the right again. And then again, that means that CH3OH is going to increase. Now the next one, the addition of H2. So I take a look here. If I'm increasing H2, so H2 is increasing, that means the forward reaction is going to be favored because it has more opportunities to react, which means again, we are going to shift right, and the CH3OH is going to increase. And then lastly here, hold on one second here. Yeah. Lastly, the addition of a catalyst, and that's the trick, right? So there will be no change. So no change here because the catalyst will not impact the equilibrium, okay? So we will not have a change in concentration of, the CH3OH. Man, it's my kid's school again. Oh my God. Anyways, okay. Handout. What a video. I probably should have stopped this, shouldn't I? My apologies. Very unprofessional of me. You are going to just read through the handout on practical applications of the Chatelier's principle, okay? So you've got, and this is I like this little infographic here. You can probably Google that, it comes up pretty quick. Anyways, read through the practical applications. It's actually kind of interesting how we do experience this in our real world fairly often. Your assignment then, you've got a sheet called the Chatelier's Principle Assignment, the answer keys on the website, and then exercise 11 as well. Okay, thank you everyone. Again, sorry for the video.